Welcome to our presentation. I will talk about protecting GNSS and all about interferences today. Topics that I want to cover are as follows: defending GNSS bands, then how to test receivers, and then how to monitor interferences, and then how to report interferences, and another topic, how to analyze the performance of different GNSS satellites, and report a case that we had last week in Moscow, which we reported to Russian officials. This is how it was, and this is how it still is in some receivers. Wide open floodgates. GPS and GLONASS bands are here, and the filter that is supposed to protect them, it's wide open. I was surprised to hear that a person is nominated to receive some award for saying that light squared hurts GPS signals. It's like you see it's raining outside and you want to research, go outside, see if rains fall on you. Yes, when the floodgate is open, everything will get affected. So this is what we started to work to protect GNSS bands, and in addition to prove that they work and also to report on areas that doesn't work because people interfere within the GNSS bands. So this is what we call J-Shield, and it protects all GNSS bands. This is the actual graph from our filter on the first band. It has the slope of about 12 dB per megahertz. It covers Galileo 1, I should say it protects Galileo 1, GPS L1, and GLONASS L1. And put that in perspective, light squared 10L and light squared 10H and 10R, which were the handsets, they are fully protected. And these precious bands are free for FCC to wants to give to anybody. This is similarly for the L2 band. There are nobody is asking to broadcast anything in this band, but this is for future. We also protect similarly with about dB, 9 dB per megahertz, and we protect Galileo E5, GPS L5, GLONASS L3, GLONASS L2, and GPS L2. This was the simple part, that we have J-Shield that protects, and this is what was thought it was not possible. And if we, that are the smallest GNSS company, can do this, I'm sure the bigger one can do a lot better. Now, as I said, this was the easy part. Next is how to show, how to test and show that it works. I'm going to skip this part because I had over 100 slides presentation at the PNT conference that I showed with 4 different tests of filter characteristics. Okay, we showed by filter characteristics, in-circuit tests, C over N0 test and zero baseline test, that I called it the ultimate test, that this works and has no negative effect on the performance of the GNSS system. In fact, we tested unmodified and modified, and the difference between the two were less than the zero baseline test, was less than thickness of a business card. It was about 0.2 millimeter. So I will go to other important issues that I want to talk about them for the first time. How to monitor interferences and how to report them, and the other topic of monitoring the performance of GNSS system that is our GPS system satellites. Are they performing as they should? And the specific case of Moscow that I talked about. So monitoring interferences, what we had before, things like this, like a spectrum analyzer to take to the field. It takes an expert engineer to use it, and not anybody can take this to the field. The other test setup that was done during PNT test is put things in an anechoic chamber, and we have over $1 million of equipment to test, and also it took several weeks to give the reports. What I want to present to you today, that we do better embedded in our receivers that will give you instant results, even remotely, to reporting to remote locations. We do two types of tests for monitoring inside the receiver. One is after the RF processing. We do RF analysis inside the receiver, and then is also digital analysis after digital processing is done. Now, first I talk about the RF analysis. Again, this is something inside the receiver that you push a button, spectrum, or the other one that I'll talk about later about cycloslip, and you will see all the things that I'm going to present to you today almost instantly, without needing any extra equipment or any additional knowledge than pushing this button. Now, the RF analysis section. This is the screen of RF analysis section that I want to spend a few minutes. The horizontal axis represents two things. One is in frequency domain and also in time domain. In frequency domain, each line is 10 megahertz. And the reason that they are not cascaded together is the topology of our display. You can imagine, do a Photoshop in your head and paste these three lines together horizontally. 10 megahertz, another 10 megahertz, another 10 megahertz. Each pixel represents 10 kilohertz, but shows the details of 1 kilohertz. What do I mean? There are 10 channels assigned to 10 kilohertz, each channel 1 kilohertz apart in parallel, and takes the energy. And we take the maximum energy and put it in that pixel. Although it is 1 pixel and every pixel is 10 kilohertz apart, we have the full information about the spectrum. The other information, which is in time domain, is the blue line, which is the AGC. But to put this in the scale is number 45 dB minus AGC that we read. Okay, so at any instant of time, this is the spectrum energy measurement, and at the same time is the AGC value correspondent to at the time that frequency bin was being measured. So far, this is two information: the energy and the AGC. This will take 3 seconds because we take every 10 kilohertz with 10 parallel channels every 1 millisecond. So 30 megahertz will take 3 seconds. And during this 3 seconds, we have the AGC plot. So this 3 seconds is if we take only one sample, one scan of reading. But in here, we scan 20 times and we average. So it will take, every line is not 1 second, it's 20 seconds, and the total time is 1 minute. And what we see for AGC, 20 times AGC, we take the minimum. And when we take 45 minus minimum, we show the maximum AGC. So you see in this, in two items that I mentioned, energy and AGC. Also on this top is the average of all 3,000 AGCs that we measured minus what it should have been. So in this information from our San Jose office headquarters, we see minus 1.7 dB less than up to that perfect. The number one next to it is the RMS of all these 20 times 3,000 AGC readings. This is another very important characteristic. When we see variations in the AGC, it means presence of some interference. Next item is the volume under the area, under this energy, which should be constant because AGC is keeping it constant. 20 means we took this sample 20 times. Okay, now these 4 items, none of them by themselves can say anything concrete. We should look at 4. We should look at AGC plot, we should look at the shape of the spectrum, and we should look at the average, this how much is below what the perfect number should have been, and the RMS. So these 4 items are the thing that we measure after the RF processing. This is the actual picture of our spectrum that we measured in our San Jose office. It's kind of calm. This is GPS L2. Here is our fault. Here, 51st harmonic of a clock inside our receiver. If you have a radio station near you, you can plug it in, and in each band will show the harmonic that may find that fall within your spectrum. Anyway, we have corrected all these. I just want to show how detailed this spectrum looks into the band, and it looks where it should. No spectrum analyzer, 30,000 or 100,000 can show such detail. This is, again, 40th harmonic of our 30.775 megahertz frequency of our display, which we corrected. So the other things are just some things are on the air. And if you see very sharp lines, is because this is the maximum of 10 megahertz. You can spread it a little bit in your mind that these are 10 pixels shrunk together and take the maximum. So GPS L2 in our San Jose office is not affected. GPS L5, there is something in the background, but still, we don't see anything important. San Jose, test 1, and GLONASS L1, it's clean. GLONASS L2, we see something in the background. This is 20 samples. Every line is 20 seconds, the total of 1 minute. There is something in the air. Is it the handshaking between CDMA or something? We don't know. This is an unauthorized signal within the GNSS band, within GLONASS L2 band, but it doesn't have much effect. I just want to say that we see such things to this detail for the first time. Now, this is not the whole picture. We will go now after signal is processed digitally, and we say, what did we expect if the system was best, and there was nothing in the horizon. This is our signal, color-coded signal of satellites as we expect according to their elevation angle. Blue means the satellite signal to noise matches almost perfect expectations according to the both theoretical designs and things that we had seen around the world. Green means 3 dB less. And red means at least 6 dB less. So this is the picture that we see in our San Jose office. This information is after the signal is processed digitally. And this is a polar plot of the same color-coded information to know maybe the satellites are blocked by buildings or something that don't think if a satellite has low signal to noise, know where it is to be able to decide why it has bad performance. Now, this is the summary of all that you saw in these previous slides. This is the deviation from maximum AGC that was supposed to have. GPS L1 is minus 1.7, minus 1.1. These are all okay. We give a passing grade. But we don't like these fluctuations. It was okay. And as you saw, there was some on the AGC fluctuation. It showed it had a pattern. We don't know what it is, but we don't need to go back to those slides. These RMS numbers, it will show us that there was something in the air. And of course, by looking at the shape of the spectrum and look at the energy, we can see where those interferences are. This is the summary of numbers after digital processing. GPS L1 was 3.8 dB lower than what it should be. GPS P1, 5.7 dB less, and there were 10 satellites for CA and 10 satellites for P. Similarly, for GPS L2, because we had only 2 of them had CA code, and all 10 had P code. These are the numbers. GLONASS, minus 2, minus 0.2, minus 0.8, and GLONASS L2 the same. So GLONASS L2 had a little interference in our area. So all these together, you cannot look at one item and make any judgment, because you may have RF has interference, but because we have 10 dB of headroom, you may see perfect picture in here. You have lost only your headroom in the RF section, means interference was not big enough to kill the receiver, but it reduced its head margin. So not looking at one number cannot make a conclusive judgment. All numbers together, if they are clean, then we give it a clean bill of health. This was another test in San Jose, and this has 100 samples. So every line is 100 seconds for the total of 5 minutes. Here, you will see the blue line because it's 5 minutes. They're compressed together. There is something going on in the background. No other instrument can show such a thing, that there is CDMA or whatever is going in the background, and it is affecting GPS within the band. Probably more than 1 dB that we were all so much worried about light squared already exists within our cities with this level. I'll show you more what exists already. This is GPS L2. It's almost clean. GPS L5, almost clean, but still we have variations in AGC, 1.7 dB variations. Anything above 1 dB, I will mark it with red. Similarly for San Jose 2, and here is GLONASS L2 in San Jose. It doesn't have, that's what I mean in here. You don't see any effect on the performance or anything because our receiver compensates for it with a 60 megahertz sampling of 8 bits and closing the AGC at 100 kilohertz and providing 60 megahertz of 8-bit to 3-bit conversion. We cover for this, but these are things that they shouldn't exist in our band, and they do exist. And look, again, this is 100 samples, means everyone is 10 seconds, it's 100 seconds. So this is a pattern that exists within our GPS bands today in San Jose, in the heart of Silicon Valley. And this is the other information about that I said after digital processing. You see we have lots of green numbers. So we are affected by more than 3 dB already. And this is the polar plot, and this is the summary. 1.2 dB variations here, 1.7 here, 2.2, GPS L1, GPS L2, and GLONASS L2. Now, we had similar thing in Moscow. If you see here, it doesn't go all the way down because it was set to 50 kilohertz sampling, so we cover about 25 megahertz band. But it will tell the story. GPS L1 gets affected, these numbers, because there were some external cable involved. So don't pay too much attention to these average numbers. We should have calibrated this. System looks clean. You see, this is the CA code that stands out even in the raw RF spectrum, and everything is clean. This is GPS L2. It's pretty bad. It's in the center of Moscow. Look at the shape. GPS L5, it's kind of okay. GLONASS L1, kind of okay. GLONASS L2, it's pretty bad. We cannot track it. We were not able to track GLONASS L2 within Moscow. And this shows the after digital part. These are GPS numbers that are mostly red, and GLONASS numbers on the P2, they're all gone. In the center of Moscow, we were not able to track GLONASS, and there was not one day. This is the polar plot. I will go through this because there were several tests. I will just go through them fast to see this is the repeated thing was happening day over and day. Okay, this is day number 2 or another day. GPS L2, GPS L5, GLONASS L1, GLONASS L2 again, and all the GLONASS signals are out. people that were doing survey in the center of Moscow had no clue that they were not using GLONASS at all, because CA code was there, and they were getting answers. We were using GPS GLONASS, and the signals were there because they all look at the existence of a satellite by looking at the CA code only. CA code tracks, everything is okay. There was, for navigation is okay, but high precision users in the center of Moscow, they were not able to use their own satellites for doing any high precision receivers. So this was Moscow 2, Moscow 3, I will go through it again. It affects GPS L2 also because GPS L2 and GLONASS L2 are near each other. This was day number 3, again GLONASS L2. The same, look, there is no information on L2 from GLONASS satellites. So, same summary. Now I will show you only GLONASS L2 in several days. This is day 4, this is day 5, and these are all 10 samples each. This is 50 samples, that's why you see the pictures are more crisp. The variations of 15 dB going up and down, and no track of GLONASS satellites. Again, day 7, or another day of GLONASS L2. So this, I called my good friend Sergei Revnivov sitting here, and Sergei, I said, Sergei, this is the problem that you have in Moscow, and he didn't know, and he told me what to do. We invited ministries of communication and the head of but Moscow Roscosmos, Sergei, Russian Space Agency General Shilov and all, and they were pretty shocked. And they have authorized everything anybody can do to find who is doing this. And this, we did it on last week, September 12, around 2 o'clock in our office. This is what I say, such a tool never existed. And this is something that exists in every unit, in the small things that you have in your hand. As Michael is going to demonstrate today, we can connect any of the receiver to anyone, any of our controllers, to anywhere in the world, and show the stuff that I was reporting to you today. These are all not artistic, artworks. These are screenshots from exact receivers that you're going to see today. Now, we have gone one step more. We want to look at the heartbeat of the patient for high precision users. What is the heartbeat? What do we measure? Garmin uses code phase. No problem. They have accuracy of many meters, and they talk about many meters of error, but we talk about millimeter. Why? Because we track the phase of the carrier. This is the artist rendition of the carrier, and when we lock in here, lock point moves around here. This is when the heartbeat is okay. If we have a little bit more interference, this may jump from this lock point to this jump, to this. This absolutely no one can notice, has no effect on low precision receivers. But this, being about 10 centimeters of error, will give the high precision users 10, 20, 30 centimeters of error without noticing. Of course, this can be discovered in post-processing software and in some enhanced RTK engines. But it's too late after you say, oh, I had cycle slips. We do this cycle slip as a measure of looking how good the receiver is and how clean the environment is. That is like looking at the heartbeat of the receiver and you say what happened, and you can track it for 1 week or as much you want, and you say during this period, how many cyclist slips I had, or this patient had missed the heartbeat how many times during the past several hours or days or whatever. This is the picture, this is the screenshot from our cyclist slip. We group, and also this is the slide that we measure the performance of our satellite system, that how satellite vendors did their job right, and how satellite is performing okay if we have certified that the receiver is okay. So what this picture is, we group the satellite signals according to their signal strength, going from 0 dB to 50. This means this is the elapsed time, 10,800 seconds. During this 10,800 times, 10,800 seconds. During this 10,800 seconds, we had average of 5.22 satellites transmitting in this bin, and it accounts for 35.88% of satellite availability. At this period, GPS L1 had 35.88% of its energy, 50 dB or higher. 45% had at 10,798 seconds, had at 45 dB, and that accounts for 45%. So this slide you will see 35 and 45 is 80 and 97% of the time our signals were above 40 dB hertz. And this says we had one cyclist slip, one satellite at this bin. So here we had no cyclist slip, and in here, this says total number of cyclist slips in all satellites. This is number of cyclist slips per satellite, and this column is number of cyclist slips per satellite per hour. So this is another indication that this environment was clean. And also this number, most important when you want to compare the performance of the satellite systems. GPS L1 get the score of 47.65 during this period. The same for the L2. Now we extended, say, let's do for the full day. For the full day, GPS L1 had one cyclist slip, the full 24 hours, had one cyclist slip at this bin, while total, we had average of 4.95% satellite in this bin. So again, if you look for full day, no cyclist slip here, one cyclist slip here, 13 at this bin, and 15 on this bin. So here is at 35 dB, 1.25 cyclist slips per satellite per hour. And it was 5% of the time. Don't look, this doesn't count because it was 5% we were in this bin. 35%, 34% here, 55% here, and all this, we had almost no cyclist slip. Majority of 95% of the time, we had nothing. And GPS L1 gets the score of 44.98. Now we go to GLONASS L1. We compare, okay? Similar thing, 40%, 41%, 16%, again, similarly, no cyclist slip. But GLONASS is 3 dB better than GPS. Of course, you can, all this, you can test yourself, and you can reset period to whatever you want. And we can also take the snapshot and we can send, as I will explain later, to any remote areas that you want. Now, GPS L2. GPS L2, because of, you know what, we don't get much above 30, above 35 dB because of encryption. So GPS gets the score of GPS L2, 31.24 dB. GLONASS L2, most of the time, is above 40 and 45. So similar, we have no problem in this area. These are in San Jose, and we don't have any problem. We can also get the same thing, combine GPS plus GLONASS and for L1 and combine GPS GLONASS for L2. Now, I want to show this to some mature audience, adult mature audience. GPS L1, GLONASS is 3 dB better. This one that I was campaigning, please don't do this. GLONASS is 10 dB better. Okay? Now, we say, we campaigned many years ago about selective availability. We were able to do something. Here, I just want to thank our Russian friends that we used to call them evil empire. They are giving us their satellite system free of charge, and they don't encode it, and they don't intend to put bomb any place. I hope my friend Gaylord was here today, that last year we had some heated discussion. I just tell this, all of you, when you leave here, please think. Please think. The policy that was made, it was pre-SA, and it was in the Cold War. They realized it. They finished it. They give us free of charge, 10 dB better. And no one in here said anything about this 10 dB. And then when Light Squared came and talked about 1 dB, the hell broke loose. 1 dB. GLONASS is 3 dB better on L1 and 10 dB better on L2 because they don't encrypt it. And then when I said, don't do this, they said something related to bombs or something. And at the same breath, they say high precision users account for $90 billion of things for our economy. Anyway, so this was end of discussion for, what did I say? Adult discussion, mature audience. Okay, how to report interferences. We have this way, all the slides that you saw in here. It can connect to any one of our GNSS receivers through Wi-Fi. You can see this, that we don't have a good Wi-Fi in this hotel. Maybe we have to go through cable, but in this conference, we brought another hot point here. It works slightly better. In our office, works without any problem. Here, you can connect through Wi-Fi to any receiver anywhere in the world and see what is going on. This is one way, via Wi-Fi to Victor VS. Another one is from via Wi-Fi to NetView. NetView is a software that runs on any PC, and you can connect through internet to any receiver in the world and see all the information that I presented to you. And these are all, if there is time, we can just show you all this today. Another thing is via Wi-Fi to our NetHub. NetHub is not one-to-one. NetHub, it's a program that connects to many receivers, and you can, in parallel, you can view interferences, all the slides that I showed you, to anywhere in the world. I mean, in parallel with many of them. This one, I like this one as the most versatile and most interesting. That all the slides that I mentioned today, you can ask the receiver to take the snapshot, and also you can say, send it to a server. Here is this spectrum setting. You say how many samples to take. You saw I had 10 samples, 100 samples. How many samples to take? What harmonics to mark around you. If they are TV stations or something, you mark them, and it will mark in all bands the harmonics of those that you have specified to see where, if those suspect transmitters will fall within. How many times do this, and how often? Every 20 minutes, or every day, or every week? And what to record? Do you want all bands of 6 GPS L1, L2, and other screens, or what? Or combinations thereof, I will talk later. Record it in there and share via FTP server. When we take snapshots, share via FTP server, and this is your server that you can set. So you take any of these receivers, you program in there what FT server you have, and you program, take a snapshot every so often. It will go to that website. It will go to that FTP server. And we have an FTP server that I'll show you. If you have iPhone or any smartphone, you can look at your browser right now and look at our San Jose FTP site and see everything that we can record. If we record now, you can immediately see it, and you can tell all your friends around the world, look at it and see. This is, if you want, JAVADGNSS.net/spectrum. Note that S is capital S. Now or anytime later, look and see everything that we talked about. So this system that I mentioned, when this information goes to a server, you can even analyze it. You say if any of the parameters that we mentioned, AGC or whatever, exceed certain limits, send emails to this manager or to this general or whoever. You are driving your car and it beeps and you say, yes, in New Jersey, in this area, our GLONASS or GPS L2 got affected, and will give you the shape of the spectrum and everything you saw. And I know iPhone shows all these graphics. Okay, so one thing that we need to do, all these monitoring things does not need to include any extra cost. We have reference stations. For RTK, we have reference stations. For Earth monitoring, we have reference stations. These features it's good to be embedded in everything, that they not only report the RTK messages and everything, also they report interferences to anywhere else in the world. The infrastructure does exist, doesn't need anything, just these features. Receiver must be used that has these features. From the user point of view, you must monitor interferences in area before performing tasks. Like pilots check their weather before takeoff. If our surveyor in the heart of Moscow, when they want to do their thing, if they first look, they don't need to ask later, why my RTK will not get settled so quickly, or why my GLONASS doesn't work. We are working with Sergey and his team to establish such system and monitor to see from where this information comes from. I want to leave you with this picture, that what is that we are suffering today because of our signals have been encoded, and we are losing about 10 dB of we civilians deserve to get if we contribute $90 billion a year to the economy. We deserve to get our 10 dB back, either through not decoding it, or better yet, something that we both agree on, to push Congress to expedite the deployment of the new GPS signals that have modernized signals. But until then, we really rely on the support that we get from our Russian friends, which I really want to thank them a lot. This Sergey, I don't know, still when he comes to my apartment, he brings his own cognac. He still thinks I've been commissioned by CIA to harm him in Moscow. Yes, Sergey? Okay, so, and this is the picture that I want to leave you with. Thank you for your attention. I'll be happy to answer any question. They said we can use a little bit more than 45 minutes that I have exceeded. Yes.
How we reported and what is the system here in USA to report?
No, as I said, this was on September 12, and after that I came to Moscow, and Sergey was not there also. When we go back, this is our first priority. Yes, Sergey? To find where. Okay, if no, yes. Yes, you can. The software does exist. Of course, the software, as always, we keep improving it too. Everything exists today, and most of these things are also patented, which we intend to defend our patents as vigorously as we defend the GNSS bands. Yes. How do we, okay, group delay distortion does not have any effect. Group delay distortion only can cause by change in temperature. I had 2 more slides expecting that you may ask this question. This is the group delay variation because of temperature, okay? Because maybe the filter shape may change according to the temperature, and we compensate for temperature variations to put this inside. Group delay variations has no effect, as I have explained in the 110 slides in the previous. So this, I was hoping somebody may ask the question if this is an issue. Yes, we compensate for temperature variations of filters. Yes? We know the interferences are in Moscow, and I have some clue from where they come from, because I'm near a big tower that most of transmitters are there. But as I said, this I saw last week, and when I reported, I got the attention of the highest ranking people in all organizations with the support from Sergey. So where it is, maybe right now there are people investigating where it comes from. And as I said, it's not in Moscow, it's in our San Jose. I showed you. In our San Jose, we have interference. And this is San Jose is a very calm area. Take this in the middle of New York, and you will see, you will have similar pictures. The thing is, every receiver has about 10, 15 dB of headroom. They don't see it. And this is few days old information that I saw. It's not unique to Moscow. I bet you take in any big cities in US, you will get many dBs of degradation because such a tool didn't exist. Who monitors this? With what? You tell me, with what we monitor our spectrums? Do we have every 5, 6 kilometers, do we have a monitor? What is our, who knows? Does anybody know how we monitor interferences within the GNSS bands in this country? Maybe, Alan, do you know? From GPS world, you cover interferences, have been for years. How do we monitor? Who monitors? With what instrument monitors? Because when we wanted to, the issue of light squared came, it took, I don't know, 24 of scientists and $1 million of equipment and 3 months of tests to verify this interferes or not. This is the first time that we have such a tool. You put it in there and in 2 minutes, or let's say in 10 seconds, you just get and you report. You can analyze in the server thousands of this in the world and report where where interferences are. And again, if we don't care about finding where the interferences are for friends of Mark Chiefs, the surveyors, they need first to look what is their environment before they starting their survey job. Okay, I think we have passed our time. Still, if you want to see anything in real time, Michael is ready to show you. Thanks a lot for your attention.